So for the next set of problems, we're just finding the domain, and I know that domain tends to be the easier of the two versus the range, but with log functions, typically the domain is the more challenging one because the range of the logs is typically all real numbers, and so it's the domain that has the issues. So if you remember back in the first video, at the beginning of the first video, we said the bases of the logs that we're going to be dealing with in this class are greater than 0, and also the base can't be 1. And we also said that since the log is an exponent, if you raise a positive number to any number, you can't get 0, and you can't get anything that is less than 0 either, so the arguments have to be positive. So fast forward to this part here, finding the domain, the argument, which is the x minus 1, has to be positive. So we say that x has to be greater than 1. Okay. Here, and for h of x, we see that the argument being x cubed has to be positive, so therefore x has to be positive. Okay. And now, really a cool problem here. You take the argument, which is 1 over x minus 5, and that has to be positive. And so here we need a bit of a sign chart. We know that as x changes, so does the sign of the denominator. But 5 is what makes the denominator equal to 0. So 5 would be one of those defining points here along the x-axis, in which on one side of 5 the fraction will have a negative or a positive value, and then on the other side of 5 it'll switch. Okay, typically. So if we use 5 as our dividing line here, dividing our sign chart into two sections, to the left of 5 we can pick any value like 0. 0 minus 5 is negative. And we know that a positive 1 divided by a negative number is always going to be negative. Okay? So this fraction, 1 over x minus 5, is negative on that interval. And then if we pick any value to the right of 5, so any number bigger than 5, let's say 7, that would make both the numerator and the denominator equal or positive. And so therefore the only real numbers that would make this fraction positive would be the real numbers greater than 5. So we would say that the domain of this function would be all real numbers greater than 5. You can't include 5. It would make the denominator 0 anyway. So there you go. There's the domain. So that's all the preliminary stuff. And now we've got we haven't even done regular log function yet. So let's do that. Maybe somewhere f inverse of x. What? Yeah, let's change this. Okay, let's do this. Let's change this to just log base 2 of x. So f of x equals log base 2 of x. We know that the domain is all real numbers greater than 0. We know that log functions have a range of all real numbers. Now, not all log functions, but when I guess I shouldn't put that right now, but after you do a few of these, you realize that most of the log functions have a domain or a range of all real numbers, unless it's a special case. And so I can't even think of any special cases right now. So until you're told otherwise, range is all real numbers. Okay, x-intercept. It's where the log base 2 of x is equal to 0. Okay, so if we want to find the x-intercept, we set y equal to 0, and then we solve the equation, this equation for x. Okay, well, when you have an equation in log form and your variable is all locked up in here in the argument, then you just convert it to exponential form. So those same equations that we were converting before, this is the reason why we were doing that. 2 to the 0 is equal to x, so therefore x is equal to 1. Okay, so x is equal to 1 is the x-intercept. Okay, well, the y-intercept then, can't have a y-intercept, can we? Why not? Because x cannot be 0. So if x cannot be 0, we have no y-intercept. And guess what? That's the asymptote. Log functions have a vertical asymptote, and the vertical asymptote is x equals 0. Now we have a key point. We always have a key point on the log graphs, just like we have key points on the exponential graphs. Remember the exponential function? Let's just remind ourselves. The exponential function was like this. Remember the key point? 0, 1. Okay. Well, guess what? Remember when we had we've talked about inverse functions? They were symmetrical with respect to the line y equals x, right? So then for an exponential function, if this is y equals, I may have said e to the x, but I meant 2 to the x, y equals 2 to the x, and y equals log base 2 of x are inverse functions. 0, 1 then becomes 1, 0, and the x-axis that acted as the horizontal asymptote for the exponential function, now it's the y-axis acting as the horizontal asymptote, and these two functions are symmetrical with respect to the line y equals x. Okay, and so that's kind of nice. We know that, and that's the graph. That's the graph of y equals log base 2 of x. Oh, and that's what I was going to say. That key point that was at 0, 1 for the exponential is at 1, 0 on the logarithmic graph. And why do we call it a key point? So you should be able to answer that. Think to yourself, why would we call it a key point? Well, it's a key point because that's the point at which, when you look at the exponential graph, the exponential function grows really, really slowly until you hit a key point. It's after that key point that the function starts growing pretty rapidly. So the y values increase pretty quickly after hitting that key point. That's on the exponential function. Okay, but the logarithmic function, notice that the y values are increasing really quickly until you actually hit that key point. And then once hitting the key point on the log graph, then you're increasing, the y values are increasing pretty slowly after that. Okay, so just the opposite of what happens with the exponential function. And so there we go there. So there's the graph of, or here is the graph of y equals log base 2 of x. By the way, if you get stuck, you can always make an xy chart. If x is equal to 2, 2 to the 1 is equal to 2, so we have the point 2, 1. The next good x value, or good input, would be a 4, because 2 squared equals 4. 1, 2, 3, 4. The next good input would be a 9, and that would be when x, and when y is equal to 3. So when x is 9, I'm sorry, not 9, 8. 2 to the third power is equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. So right up here, so the graph would look like this. Okay, so there's the graph of log base 2 of x. So let's do something kind of interesting here. Let's even more interesting than this. Let's do this. Let's graph y equals the log base 3 of x on the same plane here. We won't answer all these questions, but basically they're all the same actually. So domain range, x and y intercepts, asymptote, key point, all the same no matter what the base is. Okay. So think about the log base 3, and let's think about also an xy chart. The log base 3 is either going to be above this curve to the right of the key point or below the curve to the right of the key point. See if you can figure that out without me showing you. Okay. When we pick 1 for the input, we get 0 for the output. Log base 3 of 1 is 0. So if you haven't figured this out by now, the log base any number of 1 is equal to 0. Because any base to the 0 power is equal to 1. So you can get back. Alright. Anyway, if we pick the next best value, 3, for x, then if the input is 3, then the output would be log base 3 of 3. Well, the log base 3 of 3 is 1. So we have 1, 2, 3, 1. Okay. The next best value would be a 9. Right, because 3 squared equals 9. And so we'd get 9, 2. And so notice that to get a y value of 2 on the log base 2 graph, we had an input of 4. So at the input of 4, we're already up 2 units on that first graph. But on the second graph, log base 3, the input of 9 is where we have an output of 2. So therefore it comes down here like this. Okay. In fact, it gets closer to the x-axis over here. Okay, so it's closer on this side, but it's, so I think I may have said x-axis. I meant y-axis. I think you knew that. But the graph of log base 3 is closer to each axis. The higher the base, the closer the graph will be to each axis. They both go through the same key point, but that's something to keep in mind, because you're going to get a question like that. You're going to see a snapshot like this. Okay, you're going to see like this, like that, and one's going to say which one is the log base 3 and which one is the log base 2, and you have to explain why. Okay, and then you're also going to see one up here. You're going to have one like that and one like that, and which one is the log base 2 and which one is the log base 3. So keep that in mind when you're going through these. All right. So the inverse, though, let's take a look there. And what do we have? A couple more graphs, and then solving equations. All right. So I'll probably cover this in 3 videos. Whatever we cover in 3 videos, I won't put you through more than 3. F inverse, if we look at y equals log base 2 of x, if we want to convert this to the inverse, we switch the x and y. X equals log base 2 of y. And then we have to solve for y. And to solve for y, you convert this to exponential form. 2 to the x equals y. 2 to the x is equal to y. So that 2 to the x is the inverse. So f inverse of x is 2 to the x. And we already know what 2 to the x looks like. Just like that. Okay, and keep in mind that the domain of exponential functions is all real numbers. The range is from 0 to infinity. And I think I did this before. Y is greater than 0. I did. X is greater than 0 up there. X-intercept none. Notice how way back up here we had an x-intercept of x equals 1. Down here, x-intercept of none, and a y-intercept of none down here, but the y-intercept is 1 here. So y is equal to 1. Notice on log base 2 of x that the vertical asymptote was x equals 0, and then the horizontal asymptote is, should do that, y equals 0. Okay, and then the key point, instead of being at 1, 0, is at 0, 1. Okay, so we did already talk about that, and just to officially get that in your notes there. One other little mnemonic that I'll sign off with for this particular video is this. Okay, write this down at the bottom. Exponential and logarithmic. Okay, I'm curious, why would I write logarithmic like that and exponential like that? Tell me in class why you think I did that.